At the end of our last video, we saw that when an electric charge moves through space, it creates a new powerful phenomenon, the magnetic field. We are all familiar with it. You move a magnet, a compass needle follows. It seems like a fundamental independent force of nature pulling the strings. But what if I told you that magnetism doesn't actually exist? What if this entire force is nothing more than an illusion? To prove it, we don't need complex magnets. We just need the simplest setup in electrical engineering. A straight copper wire. Inside this wire, we have two parallel chains of charges. A chain of positively charged metal ions, permanently locked in place, and a chain of negatively charged electrons, completely still. If we place a lone proton just outside the wire, it feels absolutely nothing. The wire is electrically neutral, but watch carefully. The moment the electrons start flowing and the outside proton starts moving alongside them, it is violently pushed away. But why? To solve this, we have to bend the rules of space and time. Welcome to VastVoltage. Let's visualize the invisible. Inside our copper wire, these free-moving electrons are what we call electric current. However, we must account for a historical convention. While electrons physically flow in one direction, the conventional current is defined as flowing in the exact opposite direction. Understanding this vector is critical for everything that follows. This current generates magnetic field, or magnetic induction, represented by the vector B. This field manifests as a series of perfect concentric rings that extend outward into infinity, with their intensity diminishing as they move away from the source. To determine the exact direction of these field lines, we apply the right-hand rule. Align your thumb with the conventional current, and your curling fingers will trace the precise circular path and orientation of the magnetic induction lines. When the external proton enters this field at a certain velocity, it experiences a fundamental interaction known as the Lorentz Force. This force is highly dynamic. Its magnitude is directly proportional to the particle's speed. The faster it moves, the more violently it is deflected. Mathematically, it is the result of a vector cross product between the particle's velocity and the magnetic induction. This model is the backbone of electrical design, yet it hides a profound paradox. Since the wire contains an equal number of positive and negative charges, it remains electrically neutral. From our stationary perspective, there is no net electric force. So why does a moving charge experience a force that a stationary one ignores? To solve this, we must look through the eyes of Albert Einstein. Albert Einstein realized that the classical model was incomplete. He discovered that the space and time are not fixed universal constants. Instead, they are dynamic, and their perception depends entirely on your frame of reference. This led to a phenomenon that is a fundamental law of our universe: special relativity. To visualize this, imagine a simple rectangle at rest. But watch what happens when we set it in motion. As the object accelerates towards the speed of light, its length actually contracts along the direction of motion. To a stationary observer, the rectangle physically shrinks. This is length contraction. This happens to everything, even to a car driving down a highway. But at normal speeds, the effect is so small, you can't even measure it. Most importantly, this effect depends on who is watching. If you sit inside that moving car, the car looks normal, but the road outside looks shorter. Now let's apply this change of view to the wire and see exactly what the moving proton sees. Let's go back to our setup. we have a neutral wire and a moving positive charge. But now we will do something radical. We will look at the universe through the eyes of that moving proton. In this new viewpoint, the proton is completely still. From its point of view, it is the center of the world, and the whole wire is flying past in the opposite way. First, look at the positive metal ions inside the wire. In the lab, they stood still. But from the proton's viewpoint, they are flying backwards at high speed. And keep in mind the Einstein tool. Objects in motion get shorter. Because these positive ions are moving, the space between them physically shrinks. They get crowded, they pack together much closer than before. Now look at the electrons. In the lab, they moved at the same speed as the outside proton. But now, from the proton's point of view, they have stopped. They move at the exact same pace, so they look completely still. Because they no longer move in this view, the gap between them widens. They spread out, taking up more space than they did before. Do you see the mismatch? We have more positive charges packed into the same space, and fewer negative charges to cancel them out. The balance is broken. From the moving proton's viewpoint, the wire is no longer neutral. It gained a net positive charge. And what two positive charges do? They push each other away. It's not a magnetic puzzle anymore. It's just a simple, direct electric force. To be exact, because the particle keeps accelerating and its speed changes direction, the actual path is a complex curve. But the main source of that initial push, that is just relativity. You might assume that relativity doesn't apply to a basic circuit, since electrons inside the wire only move along a few millimeters each second. But wait, inside just 1 centimeter of copper wire, you have billions of charges. If you take a tiny, almost unseen spatial shrinking and multiply it by billions of particles, the outcome is huge. It becomes a massive physical push. We found that magnetism and electricity are just two sides of the same coin, the electromagnetic field. This is the deepest secret of electromagnetism. A magnetic field is simply an electric field that can only be seen this way when viewed from a moving standpoint. While we, sitting at our desks, see a separate magnetic push, the moving particle itself feels only the basic electric push of Coulomb's law. Magnetism is not a standalone thing, it is a combined effect, a link between electricity and relativity. But what about a typical magnet? It has no wires and no battery, yet it works. Even here, the cause is movement. Subatomic particles like electrons and protons have a feature called spin. They act as if they spin on their own axis. Just like Earth, these particles have magnetic poles made by their spinning motion. And here is a detail most people get wrong. Even though we call it the North Pole, Earth's top icy region actually acts as a magnetic South Pole, pulling the north end of every compass on the planet. At the atomic scale, billions of these tiny spinning motions align to build the massive magnetic pull. We've seen what charges can do when they are free to move, but why are they free in the first place? Why does electricity flow through copper easily, but stops completely when it hits wood or plastic? To build real technology, we need to understand the cages holding these charges. We need to look into the atomic design of matter. If this video helped you see the universe in a new way, make sure you subscribe, like and drop a comment to join our mission. Mastering engineering starts with visualizing the invisible. I am VastVoltage. See you in the next one.